Okay, so for this lecture, we're not really going to be discussing much. We're just going to continue our last lecture, wherein we talked about finding fundamental groups of some spaces. So what we did first was try to find the fundamental groups of the space, and then we femboyize it. So last time we talked about finding the fundamental groups of roses, which is a collection of these loops that loop up to a single point. We also found the fundamental groups of hyperspheres, most notably for the case of three-dimensional spheres. So now we're gonna be talking about finding the fundamental groups of fundamental group of a torus. So we're gonna find the fundamental group of a Femboy donut. If you recall what it is from the last course, FT2. But to simplify things, we're first gonna be finding the fundamental group of T2, and then we're gonna femboyize it from there. Okay, so right. So we begin with the identification space of a torus, and you guys will remember that as taking a strip and then identifying the edges like this. So first we grab these two edges, and then we bring them together to form a cylinder. And then once we form a cylinder, this becomes like this. Once we have that, we take these two circles, or these two boundaries, and then we put them together. And then this forms a torus. So this is a torus. Now you can construct a torus by taking a circle, one circle, and then we add circles along its boundary, or along it. And then, well, that's what there's two ways of constructing really: identification space and taking the directly by taking the Cartesian product of a circle with itself. But we're really going to be focusing on finding the fundamental group via the identification space. Okay, so recall the Kampen Theorem. We need three subsets from this space to find the fundamental group of this torus. And usually the fundamental group, Kampen states that the fundamental group of the entire space is just the fundamental, or the free products between the fundamental groups of two subsets of it, two subsets from it, mod some normal subgroup that's the smallest normal subgroup. Okay, so let's begin by identifying A, B, and C here. So our A space, or our first subset or subspace, is everything, or we extract a disk from it. So imagine if this is this, we're going to take out a disk, and A is the interior without that disk. So if this is T2, A is T2 without a one disk. Okay, that's our first subset. And to show that this is path connected, you just take 2 points here, and then make a curve, and then you notice that they're connected. And this is also connected because when we split it into two, really you can put them back together with a little bit of overlap on the boundaries. Okay, so that's our first subset. Now let's find B. So B this time is the edges and a small sliver or pool around the area where we take this from. So this is our space. And then this is our disk taken out. We make a small pool over here, just around it, and the corners. So the shaded area here is B, or the subset B. And they're also path connected. Because notice that if we take 2 points even at the corners, 2 points in it, and then connect them, it stays inside the set. And as well here. Now you may be thinking, oh, what if I take a point here and another point here and then connect them? Well, it's outside the set, right? The thing is that cannot exist because when we make a curve or when we embed a curve, naturally it should all fall within the set. So this is not an embedding of a curve, and thus it doesn't qualify for our criteria of identifying the space as path connected. Okay, so now we have B. B is some sliver or some part of A. Oh wait, no. B is just a shaded area, sorry. That's C. So sorry. B is just a shaded area. Okay. Just a shaded area around here. And then C is the intersection between these two. So C is the figure that I drew a while ago. Is around corners. There. So this is C, still path connected. B is also still path connected, or at least this sliver of the identification space. Still path connected. Now since all three of these spaces are path connected, we can use the Kampen Theorem and of course find the fundamental group of T2 by finding the fundamental groups of these guys, taking the free product of one of them or two of them, and then modding out a subgroup. Okay. So now you'll notice that A here, A is actually homotopic to a rose. Homotopic. So A is homotopic to this actually, if you notice. Or it takes a little bit of imagination, but you'll see that it is. B now is homotopic to a point. It's contractible to a point. We can grab a point here and then map every point or every distinct point along B onto that point. It's like squashing all of R onto a single point. So it's possible. So B is homotopic to a point. And then next, you notice that C is homotopic to an annulus, which is homotopic to S1. So C is homotopic to S1, which is a circle, basically. Because you just squash it down, just contract it a bit, widen the ring, and then you get your circle. So we can contract or retract all of this onto a circle, and that's what it is. Okay. Now, you notice that because A is equal to a rose, you recall from the last lecture that the fundamental group of this is essentially isomorphic to the fundamental group of a rose. So we can say that the fundamental group of A is isomorphic, or is equal to Z2 or Z free product itself, or a free group of two generators A, B that are an element of the integers. Okay, so now that we've identified the first fundamental group, let's find the next one. So find the fundamental group of B, since it's just a point, is 1. It's a convex subset, and you notice that it's somewhat similar to a disk. And we know that the fundamental group of that kind of thing, like S1, is 1, or actually not 1, but it's 0, but we know that it's somewhat like a circle, and it's somewhat like a convex subset, and it's 1. The fundamental group of B is 1. So phi 1 of B is 1. And now since C here is S1, you notice that B here is closely resembles S1, so that's why its fundamental group is 1. Okay. So S1 on the other hand, we already know its fundamental group to be 1, but since C is homotopic to S1, we can say its fundamental group is isomorphic to the fundamental group of S1, which is the integers, or it's a free group of one generator. So phi1 of C is equal to just Z, which is equal to free group of one generator A. Oh, not precisely A, but a curve gamma that we embed inside C. So if I draw C here, identify the edges, this, and then here. Gamma is some sliver here that runs around inside. So this part here is gamma. So it's a loop inside C. Okay. So now we found the fundamental groups of each of these spaces. Let's use back Kampen Theorem to find the actual fundamental group of T2. And this is where what I said about presentations and groups themselves, or group presentations, come into play. So from Van Kampen, you guys remember that phi1 or phi1 of T or X of the space X is equal to phi1 of A free product phi1 of B mod some small normal subgroup N. Okay, so let's just substitute the necessary stuff. So phi1 of T2 is equal to the phi1 of A, or rather Z, free product Z, free product 1 mod N. We're actually, it's actually the case that C is mapped onto A, or it becomes apparent that the image of a mapping between C and A is actually this N over here. I mean, it may not be apparent right now, but you guys would notice. And this is with a base point. So it's a base topology. Okay. And then this N is now some image or isomorphism between phi1 of C and phi1 of A. So this is the fundamental group of T2 at the base point. And okay. So all of this is just equal to a free group on two generators AB mod the image of some F or free group over this curve. That's it. So the class, so not only is gamma class, or not only is gamma curve, but it's also a class of curves that are in the fundamental group of A, and this actually represents a full travel along the boundary of the identification space. So if this is A, this is minus A, and this is B minus B, we can represent gamma as A, B, A to the minus 1, B to the minus 1. So we first travel along A, and travel along B, and travel back minus A, and then travel back minus B. Or B to the minus 1, B to the minus 1. Okay. Okay. Okay, so now we can rewrite this image we can rewrite this image as, or this fundamental group as the free group on AB mod mod the presentation, or this is where presentations come in handy. The group, so this generates a group also, or this gamma generates a group, and it's represented by this AB, A to the minus 1, B to the minus 1. And another way of presenting this, or another presentation for this group, is, well, of course, we also have all elements A, B, such that it satisfies this rule. Okay. And it also, another way of presenting it is by equating this to 1. So it can also be F A B mod AB such that equals 1. So all of that is to say, all of this is just Z2. Yay! So it's just Z2. So the fundamental group of the torus is Z2. Or the free abelian group on two generators. Okay. So I know this is a lot to take in. So alright, let's femboyize it. So what you do is just say that this is FT2. So you recall the FT2 is FS1 cross FS1. And then FT2. And in this time, this is the one femboid disk. FT1. Now, Z would just probably stay the same here. So yeah, that's actually it for femboyizing it. It would still stay the same way. You know, maybe you can think of a bunch of really thin points, which are potentially femboys, and then we pack them all together into a torus. We will probably still get the same fundamental group. So that's FT2 by 1 at a base femboy X0. Of course, gamma is a fine line of femboys that we pack together and then put inside C to find its fundamental group. And then A now is homotopic to a fine line of them, and then we form them into this formation here. Okay, so that's for torus. How about a genus 2 surface now? What if we punch a hole in the torus, or we extend it a bit? Or let me actually use an example here. If I have a kettlebell, I was actually using over this morning. If I have a kettlebell is essentially just a sphere, or S2, with a handle attached to it. Or it's actually just a torus. So, let's make an example. This is a kettlebell, which is so it's just basically we take two discs away from a circle and then attach a cylinder to each of these guys. Now, if we punch another hole and then attach another handle to it, if I do this, it's because of genus 2 surface, so I attach another handle to the kettlebell, we can essentially shrink this into just a genus 2 surface. So it's basically two toruses, mushed together by a common boundary. So this is homeomorphic to this space. Okay. So how do we find the fundamental group of these two spaces, which are kind of the same space? So to find its fundamental group, it's a bit noisy, sir. Okay. So, alright, so the next example is a genus 2 surface, or orientable genus 2 surface. So we're kind of assuming that all of these surfaces are orientable. We're not quite going to find the fundamental group of a multi-strip just yet. So we'll find first the fundamental group of a genus 2 surface. Okay. Okay, so I have my genus 2 surface over here. And its identification space is surprisingly an octagon. Yeah. This is its identification space. And the points are, or each edge is identified as such. So this, and then like this, that, this, like this, and then like this, and then like this. So this is the identification space of this space. So we just grab each side with the same, the same arrow pointing, and then we connect them, and then we eventually get this. Okay. So now, what we essentially do with this octagon is do the same thing with the square a while ago, what we did. So for A, we first take a disc out of it, and then of course we take this. This is A, and then B, we find one corner and we build a pool around it, and then B is just this block here. This is B, and then C is just the intersection between these two. This. This, and then this time the corners. C equals A intersection B. Okay, all of these are still path connected. I mean, the octagon is essentially just homeomorphic to a square. However, we would still have a different fundamental group. Okay, so it's not quite. We cannot treat it quite like a square, it's its own shape. Okay, so all of these are path connected, so therefore we can use Van Kampen again. Okay, so you'll notice that octagon is 8 sides, a square 4 sides. If a square is equivalent to a 2-petaled rose, but surely if you follow the pattern, this is, it's, or A is homeomorphic or homotopic to a 4-petaled rose. Like how this is sort of homotopic to this. This is 4 sides, okay? 2 petals. This is 8, 4 petals. Because, twice of this gives us this. Twice of 1 gives us 8 sides. 4. Let's give 4 petals. So this A is homotopic to 4-petaled rose. or a hypocycloid. Okay, so that's that. A. So that's our space A here. The B is homotopic to just a point. Like last time, it's actually kind of the same, but our ending group is still different. Although it's still Z, the set is still Z or the integers, essentially its order is different. Okay, so B is homotopic to a point, and then C again is homotopic to F of gamma. Or I didn't quite write this. Yeah. I suppose it would be the same. That's a while ago. Or yeah, an annulus. Annulus and S1. Okay, so now we have A, B, C, and again, let's find the fundamental groups and then find the free product between A and B, or the free product between the fundamental groups A and B, and then mod out N to find the fundamental group of this genus 2 surface. Okay, so the fundamental group of A is this time, since the last time, or since the rows from last time was 2 petals, we have 2 generators. This time, since it's 4 petals, we have 4 generators for our free group. So the fundamental group of A is equal to a free group on A, B, C, D. 4 generators. And then like last time, since this is homotopic to a point, its fundamental group is just 1. So the fundamental group of B is just 1. And then lastly, the fundamental group of C is F of gamma. Or at least it's, oh no, it's not really equal, but isomorphic. So it's not an exact equivalence relation, it's just somewhat of an equivalence relation. So F of gamma. Where gamma, of course, is a curve from a class of curves that we embed into C. You guys recall? So this small sliver of line here is gamma. And then we have a class of these curves. Okay? So this time, gamma doesn't just represent, travel along this, but gamma represents a travel along this octagon. And each of these sides that we identified use A, B, C, and D, and then their inverses. 4, and then their inverse makes 8. 8 sides, right? Or 8 travels. Or 8 actions. So if I have a point here, travel first here, and then here. And that's represented via these symbols, A, B, C, D, etc. Okay. So now let's make a representation for F of, or F of gamma. So that's just isomorphic to the presentation A, B, C, D, A to the minus 1, B to the minus 1, C to the minus 1, D to the minus 1. Which is also isomorphic to A, B, C, D. So the quadruplet, such that it satisfies this. C. Or no, sorry. A, B, C, D, A to the minus 1, B to the minus 1, C to the minus 1, D to the minus 1. And that could also equal to 1. Okay. Now we have all of this. Oh, wait. this is the rule. All right, now we have these fundamental groups. Let's find the fundamental group of the space that we were looking for, or for this GS2 surface. Okay. Okay, so that Kampen Theorem tells us phi 1 of x is isomorphic to phi 1 of A, free product, phi 1 of B, mod n. And we've noticed time and time again that the fundamental group of C is n. And because this is somewhat like the previous case, that becomes apparent, that n is the fundamental group of C. And in fact, yes, it's the smallest one, because it's literally the intersection between two big groups or two big subsets. The fundamental group of C is essentially a fundamental group of the smallest space we can construct from this, and just intersections and stuff like that. And that's why the fundamental group of C qualifies as n here. It's the smallest normal subgroup, and so we're going to mod that from the product between A and B, or the fundamental groups of A and B. Okay. So, okay, what am I doing exactly here? What I'm basically showing you guys that this GS2 surface is not equal to a torus. I'm giving you guys a more in-depth and rigorous way of showing that this surface here is not the same as a donut. I mean, it's obvious, you can see two holes, right? But we're making a rigorous argument to show that it is not by showing that a fundamental constant or fundamental characteristic of it is not the same as the fundamental characteristic of some other space. Okay, so, alright, so let's just plug the stuff in, right? So, phi 1 of this GS2 surface, T22, I'll just call it T22, okay, is, alright, I'll just write is isomorphic phi 1 A, or you receive it here, the free group of 4 generators, free product, phi 1 of B, which is 1 mod F of gamma. That's just isomorphic to FAB, CD, asterisk 1, and then the presentation, mod the presentation, ABC, e to the minus 1. Alright, so, okay. So this over here is the fundamental group of our original GS2 surface. Now you notice that this is not abelian. For any two elements here, we compose them together. They're not the same as if we switch the positions. So what do we do when a group is not abelian? How do we, for lack of a better term, abelianize it? So an abelianization is basically a map where we take our non-abelian group G and take it to some modding, so G mod a commutator of G in itself. So what would this be in our case? Now I won't go into specifics of the calculation for the abelianization of this, but we'll skip the results and say that's abelianization, which is FAB of A, B, C, D is Z4. I mean, you notice now that last time our free group of two you notice that last time for the torus, our free group was of 2 generators, so it's Z2, right? Because well, Z2 is defined at least to be Z cross Z. Wherein, this cross product, of course, takes two elements from Z and then you put them together, two distinct elements at least. So this time, since we have four generators, it would be Z4. But the reason why I didn't put Z4 here is because it is not abelian. Z here is strictly abelian. I mean, it can be non-abelian, but in this case, it's strictly abelian in our case of concatenation. So, because concatenation works somewhat like multiplication, and abelianness or being abelian is an important property when it comes to this thing. So it's important to abelianize the group because this is not directly abelian right now. But once the dust settles and we do perform the calculation to abelianize it, we find out that all in all, the full and abelianized fundamental group of the genus 2 surface is Z4. Alright, so okay, now that we found all of this, let's femboyize it. So it's kind of trivial to femboyize it. We just I mean, in the previous example, we can femboyize it by simply replacing Z with F, right? And instead say that Z is some representation, right? And that's kind of the reason why I use Z here in these examples, because we can just directly use we cannot just directly use the universal femboy set because that's not precisely, it doesn't precisely have the same structure as Z. It more of has the same structure as R, where in case it's not really a group under multiplication, right? Because we would have some stuff who don't have multiplicative inverses. Okay, so, right. So, we have a new name, or we're gonna term a new thing for a two-hold femboy donut. So, a genus 2 surface, we will denote via F2 T2. So, a genus N surface, or genus N femboy donut, is denoted by Fn T2. So, for example, Fn or F3T2 is a three-hold donut. Yeah. So it's homomorphic to this, or it's exactly this, and then F4 is 4 holes, and so on and so forth. 4 is this would be 4. Add another hole, we get 5. You guys get the idea. So it is here in this lecture that we introduce a multiple genus or multiple hold femboy donut. And this is the case for Z4 for this. And you notice that there's a pattern now. Okay. Previously we had one hole and its fundamental group is Z2. Now that we have 2 holes, its fundamental group is Z4. How about 3 holes? 4 holes. Well, for 4 holes, I mean, you notice that it's progressing in an even order. So it's actually logical for us to assume that for a genus 4 surface, its fundamental group could possibly be Z8. Possibly. Though it's possible that it's not abelian, but we have to still abelianize it. But in the end, if we do abelianize it, it's possible that we get Z8. So that's what it is. So each of these guys, each of these elements now is a, I believe it's an identification, or it's a line of femboys that we identify to be the same in order to construct this space. Or it's a travel along them at least. Okay, so each of these, don't think of as a single entity, but as a movement of a point that's on, one of the vertices of, or the starting vertex of our identification space. So, yeah, this is it. So this is the genus 2 surface. Now, to conclude the lecture, let's extend this concept to category theory, shall we? Now, we recall that the concept of free groups is some morphism between the category of all sets and the category of all groups. So, the concept of finding or calculating the fundamental group of a space is essentially a mapping between, or not really set, but the category of all base topological spaces. So we take all, so there's a morphism between this space or this category of all base topological spaces and the category of all groups. And like that, and so, well, like that notion, right? This notion of using Van Kampen to find the fundamental group is called a push out on set, which is the category of all sets, and it is also a push out on GRP, which is the category of all groups. And yeah. So that's the category theory version of it. It's a push out over these two sets or these two categories. Sorry, keep saying set. So that'll be it for this lecture. I know it's not quite as long as the other lectures, but we finished up our discussion on the on finding fundamental groups of those spaces. So any questions?
Is a cyclic group a belt?
Cyclic group?
Yes.
Not all the time.
Not all the time.
That's for group theory, sir. This is algebraic topology. So, that's it?
That's it.
Alright. So, this is a good place to stop.